Welcome to section 3.3, Measures of Relative Standing and Boxplots. This is the final section in chapter 3. The key concept here is that we're going to be introducing z-scores, but we're also discussing percentiles, quartiles, and boxplots, but we are introducing z-scores here, which will continue to show up throughout the statistics course. So we'll be going through the following vocabulary and important terms and also using our calculator. So let's start with the basics of z-scores. A z-score, sometimes called standard score or standardized value, is the number of standard deviations that a given value is above or below the mean. So essentially what a z-score does is it tells us how it differs or varies from the mean. And why is that helpful is that we are constantly talking about all different kinds of data values, different numbers, different meanings, and it's very hard to standardize the value. Like one quick example is if we were to try and compare SAT and ACT scores, having a 1500 on an ACT doesn't make any sense. And so having a standardized scoring system or a z-score can help us standardize the score itself and then be able to easily compare it. So that is why z-scores are so great. This is super, super important. When we round z-scores, we round to 2 decimal places. And when we start to deal with z-score tables, we'll be looking at 2 decimal places. So important properties of z-scores, it's the number of standard deviations above or below the mean. It's expressed as a number. It's not like centimeters or units of any particular measure. We are still talking about significantly low and significantly high. Significantly low is still -2 or below, or 2 or above is high, significantly high. And if an individual data value is less than the mean, it's going to have a negative z-score. Less than the mean would be negative z-score, which means that the mean represents a z-score of 0. So let's look at an example here. Which of the following 2 data values is more extreme relative to the data set from which it came? So again, we can't just compare 4,000 grams to 99 degrees Fahrenheit. Those things don't really compare. They don't make any sense. But we can see which is more extreme if we compare each of them to its own mean. So how we're going to do that is we're going to standardize it by finding the z-score for each. So the formula for a z-score is z is equal to that data value minus the mean divided by the standard deviation of the sample. So in this case, our data value is 4,000. The mean is 3,152, and the standard deviation is 693.4. So make sure you type the entire numerator and then hit enter and then divide by that number, and we should get a z-score of 1.22. Let's look at 99 degrees. So our z-score, we still follow the same formula. We're looking at 99, but the mean is 98.2, and the standard deviation is 0.62. And when we type that into our calculator, we get 1.29. So which is more extreme? Well, which one is larger or further away from the mean? In this case, larger because they're both positive, but 1.29 is a little bit further away from the mean, 0.07, so this one is going to be more extreme. And for those of you that are visual learners, I'm just going to put up this interpretation. You can read it and press pause, or you can just move on with me. And then go ahead and give this one a try. Press play when you're ready to see the solution. And there you go. So we can use z-scores to identify significant values. Now remember that significant values are those where the z-score is less than -2, so we're going in this direction, or greater than 2. Again, our mean is going to be a z-score of 0. So the lowest platelet count in a data set is 75. Is that value significantly low? So that's what they really want to know. Is it low? Significantly low. So we're going to use a z-score to figure that out. Same formula. So we're looking at the value of 75. When I look at the mean, I'm like, oh my goodness, that seems like very significantly low. But the standard deviation is 64.2, so maybe not. But when I type that in my calculator, I get -2.65. That number is less than -2, so this is significantly low. And maybe you're someone who needs to see this more on like a number line. So you've got 0, 1, 2, -1, -2, and then -2.65 would be over there. And that is within that significantly low to the left of -2. And again, for those of you that like to see it visually, you can follow along there. Pause it if you'd like to read that. And then try this one on your own and press play when you're ready to see the solution. So even though z-scores are the most important concept of this, because we're going to build on that for the rest of the course, we do need to talk about percentiles, quartiles, and box plots. Now, how come we're talking about them in the same chapter? A z-score and percentile and quartile, they're interesting because they're describing the location, but they describe it in different ways. So a z-score measures position as it relates to the mean. So the z-score is relative to the mean, where percentiles and quartiles are relative within the same data set. So they're describing the location within each other. Percentiles they sound a lot like percent, and they have the word percent in it, but percentiles describe the location. If you're in the 40th percentile, that means that there's 40% of data is below you. And it just kind of gives you an idea. So if you're in the 99th percentile, that means that 99% of the data is below you. So the percentile gives you a locator as it relates to the rest of the data set. You can find the percentile of a specific data value by doing the number of values less than. So not the value itself, but how many data values are below that data value, and then divided by the total number of values. So again, we're looking at the number of data values, not the actual data value. So let's look at this example. The airport Verizon cell phone data speeds are listed below. We've seen these many times. And they want to know the percentile for the score of 11.8, or the speed of 11.8. So how we find a percentile is we want to know the number of values less than, and I'm just using symbols, less than 11.8 over the total number of values. So let's see here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across. 1, 2, 3, 4, 5. So there's 50 total data values. And so how many data values are less than 11.8? Well, there's 2 rows. So that's going to be 20 data values. So when I divide 20 by 50, I get 0.4. And they say multiply by 100 to get it to be a percent. Or as we covered before, you can move the decimal over twice. This is the 40th percentile. And again, if you'd like to read a little bit more about that, you can here. But basically, the 40th percentile says that 40% of the values are below and 60% are above. 11.8 divides us between 40 and 60. Go ahead and give it a try with these 2 data values. And there's the solution. Now, we're going to use a little bit more notation here, and the reason we do that is because what happens if we have a percentile and we want to know what data value it corresponds to? So this is the procedure to do that, and it seems really difficult and hard, but we're just going to take it piece by piece here. So referring to the sorted data, so super important, step 1 here, sort the data, arrange it in order from lowest to highest. Find the 40th percentile denoted by P of 40. So you're like, duh, Molly, we just did this. I know what the 40th percentile is, but we're going to go backwards, okay? So the data is already in order. And now we're going to use this formula to compute. And again, n is the number of values and k is the percentile in question. So let's take a peek here. So we're looking for L. And to find L, that's k over 100 times n. And k is the percentile being used. Boom. And n is the total number of values. Okay, so let's take a peek here. So our k is 40 over 100, and we know that we have 50 values. So when I type that into the calculator, I get 20. And let's go back to here. So I got L is 20. Is it a whole number? Yes, it is. So to figure it out if it's a whole number, the value of the percentile is midway between that value and the next value. And then I add those two values together and divide by 2. Sounds difficult, but let's just take a peek here. So what is the 20th data value? Well, I know that these are in rows of 10, so I know that the 20th data value is 11.6. And to get the actual data value, I go midway between that value and the next value. Midway between 11.6 and 11.8. So I do 11.6 plus 11.8 divided by 2, and I would find that the 40th percentile is 11.7. Now you're just like, we did it and it was 11.8. Yes, but this is giving us kind of our best approximation here. So again, if you want to read through these, I'll leave these up for you. And then you go ahead and give this one a try. Press play when you're ready to see the solution. And that concludes part 1. When we come back to part 2, we'll be doing quartiles, 5-number summary, and box plots.